why would you care about this thing? And we're going to look at three discrete distributions, the binomial, the Poisson, and the hypergeometric. And I've got three examples. Well, I focus on the binomial and Poisson because this was just like that one, just with a minor difference. And I work them all by hand, so but they're in here. They're loaded up as a word. And then the last one I also do by Excel, so you can see both ways. And then for my dumb statistics thing, I'm going to talk about the June birth and being predisposing you to anorexia, and because that ties directly into the binomial distribution. So it'll be a good connection for you to see how you can use these things and also how you can misuse them. And so there. And then I also want to mention R, the R language, because I'm teaching this from a by hand or Excel perspective, but you may need a more powerful statistics package, and R is free, and R is academically very well vetted and is showing up in most of the statistics classes, statistics departments. It's used a lot. So I don't want to teach R, but I would be remiss, I think, if I didn't make you aware of it. So what I chose to show you in that, and I'll just flick it up real quick probably at the end, is remember the box plot? And we struggled with making a box plot in Excel. It was terrible, it was dumb. I did a box plot in R. And to show you how easy it is, I haven't used R. I was aware of it and I'd seen it. So this week I downloaded it. That took all of 3 minutes. It was a real small download. I read one little page on how to make a box plot, and within 10 minutes I'd made all the box plots I wanted. And so if you guys need a more powerful package, got some more statistics you got to do, I would suggest looking into R. It's free. There's websites all over the place. There's intros, there's book. I got a book. I stuck all of that on the website under a folder called R. So if you need some more statistics power, there it is. But we'll still teach the class, of course, from Excel and by hand. But I felt like that had to come in any statistics class. So with that, let's do the discrete, and I'll stop back and forth once during the PowerPoints to break off and show you in Excel. So I think you'll enjoy this lecture. I hope it'll make some good sense to you. So we're going to learn about discrete distributions, like I said, and how to get the mean and the variance of a discrete distribution. And they throw in their covariance, and that's a little, part to use. Also, I just didn't list it in my things because that's not my focus. Then we're going to do the binomial, hypergeometric, and Poisson, and then and apply just some problems in. I've got, like I said, 3 examples, and I've got another example I've made up too. So I think you'll understand this when you're done. I think you'll like it. So remember again, just to refresh yourself, we've talked about discrete and continuous variables before. So this is the discrete side. Chapter 6 is continuous distributions. And for one, why do we even care about a distribution? Why would I need a distribution? Well, you need to be able to look at what you've done statistically, whether it's an average, a mean, a variance, or a histogram, and you need to compare it to something else. And so if I make a sample and make a measurement, where does this lie within my statistical thoughts? Was this probable? Was this improbable? And that's the big question we kind of want to ask, right? If you make a measurement, just like the June baby thing, we've done some studies, we've done some surveys, we think that predisposes you to anorexia. Well, is that probable? Are my results sensible in the statistics viewpoint? And how do you do that? Well, one way to do that, the best way, is to compare it to a distribution. What distribution? Well, other known distributions, or different, normal distributions, or generic distributions, and see where your statistic falls. So we have to have these distributions so we can understand the process, understand our measurements, understand our samples, understand our results, and make inferences about our results. So again, the contrast, remember, discrete was something you could count, right? And continuous was something you measured. So, annual salary, weight, height. Discrete might be the number of things, the number of marbles you pulled out, the number of machines working or not working, the number of number of radioactive decays in a time period, those kind of things. Accounting. So we're going to do the counting ones. And this is, yeah, you know, it's interesting that they show you a picture. Yeah, because discrete, right? They have discrete values. That's how you can remember. Continuous could take any value. So that's next chapter. So yeah, here, examples of discrete things. Yeah, roll a dice. You know, how many times did you get a 4? Toss a coin, how many times you get heads? Or an example later on in the few graphs, how many times do you get head and a tail, or something like that. So that's the kind of things we'll be working with. So you might need to construct some probability distribution for a discrete variable to do, like I said, to make inferences, to compare your statistics to what you would normally see or what you expect or what you would like to see. And so, well, how do you do that with a discrete set of data and a discrete? How do you make a discrete distribution? Well, here's an example. Let's look at students taking classes, and we've got we've studied this probability comes, say, from our knowledge. You know, okay, we know that in general you have 40% of the students are taking 3 classes. You know, 20% are taking 2. There's your known data. Of course, you notice, as usual, this adds up to 1. You know, we don't have any missing data or something. And so the question is, what's the average of this? Or, you know, where's the mean? What's the variance? How can you come up with some statistical measurements for this distribution? And so, can we calculate that? Here's another example, and we'll do that in a minute. I think they do it on this one because it's easier. Yeah. So here's the coin thing. Yeah, we're tossing a coin twice, and we want to know what's our number of heads. So we have 4 possibilities. We can get none, we can get 1 2 different ways, or we can get 2. And so what does the probability look like? Yeah, there's a 25% chance we got either of these 2 outliers and a 50% chance that we got the one in the middle. So now they've actually got a picture of the distribution, like a table in the picture. And we'll play with some of the pictures in a minute. Okay. Oh yeah, so let's look. So what's the mean of a distribution like that one we saw, the coin tossing, the one in the previous slide? Well, the mean, the expected value, is just each of the occurrences that you could have times the probability of occurrence. So like in the 2 coin toss, remember we had a 25% chance of getting 0, we had a 50% chance of getting 1, and a 25% chance of getting 2. So hey, 25% chance of getting 0, 50% chance of getting 1, a 25% chance of getting 2. So the mean, or the expected value of that particular statistical process, is 1 head, right? That makes sense, right? You think about the picture we had, we could get the 2 tails and the 2 heads, but in general we had a much greater chance of getting 1 head. Okay, so that's what you would expect, the mean. Now notice again your notation, they've got the mu, because this is a population, we're not taking a sample. Remember, the Greek letters refer to a population. Again, from your perspective, you just know we're talking about an average or expected value. What do we think we're going to get? And of course, you know what's coming next. We need a variance too, right? Or standard deviation. Because remember, as we've always discussed in our distributions, we can have a real narrow distribution has the same mean as a real broad one. So we've got two characteristics we always want to discuss, at least 2, an average and a spread. So what's the spread? It's the same as you would have calculated with that we've done all year. Each value minus the expected value, square the difference, and multiply by the probability, and then the standard deviation is just the square root of it. All right, so let's see. We can calculate that on the next page. Oh, it'll be there. Oh, I touched the pad. Sorry. I do that all the time. I always disable those touch pads on mine. That's big thumbs. So let's see. So we tossed 2 coins. X was the number of heads. So let's get the standard deviation. Okay. Remember, our mean or our expected value is 1. So here we go. 0 minus 1. This is the 0th. Each of the possibilities, you have 0, 1, or 2. Here's your expected value and your probability. Expected value, probability. So the standard deviation is 0.707. That's a measure of the spread. So very simple way to calculate these things. So now we're going to switch gears and talk for a minute about the covariance. So one of the ones, covariance is a way to measure, like they say, the strength of a linear relationship in between two discrete variables. Okay, so you know what they're going to wind up doing. It's going to look like the variance, except instead of the x minus e squared, it's going to have an x minus e and a y minus e type thing. And so positive covariance means, yeah, you got a positive slope, and a negative one means you got a negative one, and you know that's the relationship between x and y, just like the slope. So here, yeah. So x minus expected value of x, y minus expected value of y. That's the probability. So x is a discrete variable, y is the other discrete variable. The probability is the occurrence of each of them. Yep. That from a y. Okay. So let's see. Here's an example. So we've got an investment. And I'm going to use this a little bit to try to, a part of these view graphs here in this next 4 or 5, they're trying to tie this to a business relationship, you know, a business type class. So they're going to do an investment, is what they're going to push this to. I generally don't, you know, I generally try to teach this more from a broader perspective. But that's, so the next few, if they seem like, well, they're not flowing with the distribution, that's what's happening. Odd, isn't it? Don't be sweating. I sweat too much anyway. And I was going to make a comment too about the homework. I guess before I forget, I think that one problem in chapter 3 refers back to another one, and then I sent out some answers. And I think the problems in the book are different. In your all's electronic book are different than what's in mine. So I was trying to think of how to deal with this. And what I decided to do, I think, is if it refers back to another problem, go with the flow and do what you want. You know, if you want to work the other problem and then discuss it, that's fine. But if you want to just discuss your answer in the context of what they're asking, you know, like that one, I think they were asking, compare it to some other results. If you want to just discuss and say, well, it seems like this one is larger than that one because of this reason, that's fine with me. You know, and I'll grade what you work. So I don't. But if you want the answers for the other problem, I can work them and send them out. I didn't realize there was a difference between the electronic book and my book. And I'm hoping that I'm going to try to look ahead and see. I hope that doesn't cause us any trouble. But I hope I haven't picked problems that I didn't want you to work. Is I guess what I'm saying. You know, because I try to pick ones that reinforce things. I hope they're that. Have you noticed, you guys that have worked far enough ahead, have you noticed that there's a significant difference? It's just the numbers are different?
Just that chart missed that one number.
Well, I've noticed that just in between the editions, there's difference in the numbers. Because I've worked several of the problems out of the previous edition, and it's the same problem, but they'll have tweaked the numbers just a bit, or they'll put question B where question C goes, and question C, and I was like, why would you do that? But anyway, work on, I'll try to look ahead, but work on I've assigned. If it refers back to something, you know, just discuss it, if you will. But don't use too much latitude, like that thing. You said that thing on the internet that time where they always have dumb answers on tests, and they had one kid with the geometry test, you know, and it had this on it. It says, name these shapes. Did you see that one? And the person had done, you know, zoo and building and France. You know, use your judgment, but don't quite go that far. You know, maybe it'll work. But I know I thought that was pretty good. That's hard. My daughter would do that. She would say, "You told me the name." Say, "Well, I guess I think that was odd." So anyway, yeah. So back to the money thing. So what we're trying to do, we're trying to find out with this covariance, are these funds, are the trends in these two funds related? So you're asking yourself, you know, you know how you could use that, like if we had a digressive fund and a bond fund, are they negatively related or positively related or not at all? And so you've got sort of a weenie fund, I guess, a passive fund and a digressive fund, and you've got the probability that the return on a $1,000 investment looks like this during these discrete cases, whether it's a recession, a stable, or an expanding economy. Again, you know, these add up to 1, and so that's the probability that these things occur. So here, yeah, you lost, you gained. So you can tell by looking that they're going to have a positive relationship. They're going the same direction. So let's calculate this covariance and see. So hey, first it's good because it shows you, hey, what's the expected value of the first fund? You know, each of the loss, the probability, the gain, the probability, the gain. Expected value of the second fund, the loss, gain, probability, gain, probability, gain, probability. Okay. So now, what do you think about that? Yeah, the weenie fund, the more passive fund, has an average return of $50, depending on the economic conditions. The aggressive one had a $95 return for 1,000 invested. So, you know, just looking at the expected values, you're going to say, well, hey, I'm choosing the aggressive one, right? But you know what's coming. Well, we got that. There's more than just the mean. There's the spread, which is representative of the risk. See, so let's look at the spread, the standard deviation, just like we did before. Each value minus the expected times the probability in the square root. Each value minus the expected times the expected probability in the square root. And so again, exactly what you would expect. You know, the more aggressive fund has a broader spread, indicating more risk. Has the possibility of actually having a negative return in general, right? Because it had an average of 95, but or a mean of expected value 95, but a spread of 193. So yeah, you knew that. Yeah, the more aggressive fund is more risky. But here's a way to show it. Let's see. So let's do this covariance too to calculate: are they trending together or not? So remember, it was this is the X fund, the passive fund, the aggressive fund, passive, aggressive, and each of the probabilities. So covariance is 8,000. So since it's large and positive, yeah, there's a positive relationship, positive correlation between them. Yeah, so they're going to rise and fall together, makes sense. So that's a use of the covariance. Now, a little bit of algebra with the discrete distributions or any distributions. So if we have two random variables, you know, whether it's a time and a measurement or something like that, you add them together, well, and they each have different means or different expected values, the new mean is the sum of the two means. It would seem logical, but the variance is not just the sum of the variances. You get this term in between, which you know, it to me is reminiscent of the the A plus B squared type thing, right? You got that squared, and the term kind of in the middle, although not quite, because if it was reminiscent of A plus B squared, you know, that would be 2 sigma x times sigma y. So it's a little different, but we'll use this later on. In fact, I'm not sure why they threw that in there now, because it doesn't play into the rest of the chapter yet, but we do wind up using it later on. So back to the investment stuff. So now that we have, we can use that. No, I know why we do that, right? Because you may put two funds together. So we've got a return. We want the expected value and the standard deviation of an investment portfolio that combines multiple funds. That's why they threw that in there. So we want to maximize the return and minimize the risk. Yeah, of course you would. So let's see. So we've got two funds, X and Y, like we had before, maybe a passive and aggressive, and we're just weighting it. You know, how much are we going to invest in one, and then the rest we're going to invest in the other, and then the standard deviation gets weighted. Yeah, one squared here, and there's one squared there, and both of them in there. Now it follows a logical pattern, and we could derive these, and I think we would be wasting class time. You can go through, do the math, do the expected value, do the variance, calculate it out. I don't think it's worthwhile. Although I'll put some things like that online sometimes for you. So here's our two portfolios. Remember our two investments. We had the passive and the aggressive, and each of their spreads. And so we're going to put 40% in X and 60% in the Y. That was that. So, yeah, so our expected value is 40% of the 50, 60% of the 95. And then our standard deviation, that was the 40% one, which was the weaker one. 60% was the stronger one. And there was the covariance. So, yeah, you can see if you mix your investment, yeah, you mix your expected value and you mitigate some of your risk. So hey, yeah, that's mutual fund. Right? Yeah, you're not going to get the huge gain of the risky stock or the small gain of another when you're in the middle, and you lowered some of your risk. So that was the business connection here. Now back to the statistics. So here's where we are. We're going to look at three discrete probability distributions: binomial, and Poisson, and hypergeometric. In the next chapter, next time, we got the continuous, the normal, the uniform, and the exponential. So no more of this today. So let's see. So first one, the binomial. So we want to kind of motivate it. What good is it? I'll switch back out and play with it. So what? So the binomial, you have, you're going to make n observations or n samples. You've got some process, and so, and they're given examples. Yeah, we're going to toss a coin 15 times, or we're going to take 10 light bulbs out of a process, maybe a warehouse or out of a manufacturing process. And each observation is categorized as to whether, they call it an event of interest. So for example, an event of interest with the coin toss might be getting ahead, like the first question we had. The event of interest with the light bulb might be defective or not defective. The event of interest in here might be the birth month. If you're looking at a particular month, say you knew all of these people had anorexia. We're not looking for that. We're looking for what month were they born in. So maybe the event of interest might be February. Is that a problem? Okay. And so you either have the thing, the characteristic, or you don't. You know, I took a sample. It was either a head or a tail. It was not. Or I took a light bulb out of the manufacturing process. It was either defective or not defective. I have a bunch of machines operating. They're either broken or they're not broken. That kind of thing. So they're mutually exclusive, collectively exhaustive, and you have the probability of the event of interest occurring is pi. Okay. And then the probability that doesn't occur then is obviously 1 minus pi. So like in the coin toss, the pi, the probability of getting ahead is a half. But in the birth month thing, the probability of being born in February is 1 in 12. Okay. And we'll use this. I'll show it to you and it'll be more clear when we make some calculations. So one of the assumptions is this doesn't change from sample to sample. Coin toss is always 50-50. That's important. Or if I'm looking at a bunch of machines, the probability that they're broken doesn't change as we go along. That's important. Yeah, so there it is. Yeah, so it's a constant probability. So now what we want to do is ask ourselves, well, you know, I'm going to make 15 coin tosses. What's the probability that I get 3 heads in a row? What's the probability that I get 5 heads total? Those kind of things. These kind of questions are answered by the binomial distribution. And yes, each time they're independent. The outcome of one event doesn't affect, one sample does not affect the other. And there's 2 ways that you get that. You either have an infinite population that you're sampling from, so that when your samples aren't affecting each other, or if you have a finite population, you put the things back in. So the coin toss is obviously infinite. You can toss coins forever. But if I was sampling, say, from a bucket of marbles, and I was trying to find out how many black ones I got out, I need to throw the one back in. If it's not, if we're not doing replacement, that'll be the hypergeometric distribution. It's a slight little modification to your probabilities. Okay, so here's some applications. Yeah, you got things either defective or acceptable. Machines working or not. Yeah, winning a contract or not. Yes or no. You can see what we're doing. Either or type thing, accept an offer or reject it. The pi or the 1 minus pi percentage. So let's see. So yeah, so here we're going to, our event of interest is obtaining heads, tossing a coin. We're going to toss the coin 3 times. How many ways can you get 2 heads? Okay, get 2 in a row first, split them to it. So there are 3 ways we can get heads. That's easy, but you know, what happens if we had a bunch of things? And so they've got that counting rule we had last week. So if you need to count, we're selecting X objects out of N objects. That's the one we did last week. So let's see. So for the coin thing, well, here's Baskin Robbins. And how many 3 scoops ice cream cones can we make? We have 31 flavors. So let's see. 31 flavors. We're going to put them together. 3 combinations of 3. Oh, we've got almost 5,000 different ones. So it's giving a way of how to, you know, how to count your possibilities, so you can determine, you know, what was my probability, or if I'm going to get 2 or 3 in a row, you know what, I can use it in here. There. So the binomial distribution has that. The total number of counting there, you know. And this is how many you want to get in a row, right? You know, or not in a row, but how many positive ones you want to get, and that's how many negative ones you expect to get. So you can kind of see how it occurs, right? If pi is my probability of getting the event I want, and I'm looking for x of them to occur, yeah, it's going to have pi to the x, and then but 1 minus pi to the n minus x times it has to fail. So there's that problem. So it's a product, you know, you think about that, and then this is divided by the total number you could have. So let's see, here's the coin flipping thing we said. X is the number of heads. Yeah, let's see, X is the number of events of interest that will happen. Whether that's 0 heads, 1 head, 2 heads. This is how many times you try. It's probability of interest. So let's see. Flip a coin 4 times. X is the number of heads. So we're going to try 4 samples. It's 50-50 whether we get a head, so it's 50-50 whether we get a tail. And now we would like to ask ourselves, what's the possibility of getting 0, 1, 2, 3, or 4? So let's see. So they'll do an example. Then I'll flip over and do an example too. I don't think they would do that. I thought they did it. Let's see. Let me do it, because I did it. Here, let me get out and show you. And then I'll be able to tell you how you can use this. Don't forget. I'll sit there and look at the screen, wait for it to come back. Oh, no. Okay, there. Okay, so this is that question right there. Scroll it down a little bit so you can see it. So this is your flipping a coin. We're going to flip it 4 times, and we're asking ourselves, what's the chances of getting no heads, 1 head, 2 heads, 3 heads, or 4 heads? And so the end, we're going to flip it 4 times. Actually, it's not quite. You're not going to get 0 heads, are you? I was going to use this for a different example, but I was frustrated that they didn't calculate that. I'm sorry. Let me switch my example here, because it's not going to work with the head. You're not going to get 0. So what I was going to use this for, because it's a similar example, and this is the time I was going to put it anyway. I use the binomial distribution in it with a discrete event simulation. And that's another thing you guys need to learn about going through this class if you haven't. If you've never used discrete event simulations, there's software that you can use to model things that occur discretely. And that's a good point to talk about in this class on discrete distributions. So if you've got things that happen at discrete times, like exactly what happens in the manufacturing environment, right? Where you got people arrive, parts come in, you put the parts together, something's made after a certain amount of time, it goes down, it goes to the next stage, gets loaded in a box and shipped. These are all things that are happening discretely, as opposed to things that are happening continuously, like say a heat transfer problem, right? You know, I turn some heat on, I'm heating up this blob of metal, it's going to heat up, it's going to melt. That's all a continuous process. There are pieces of software that allow you to model discrete systems really simply, so that you can have delays and have things happen and deal with the logic. You might want to use these sometime if you're modeling a manufacturing process or modeling something that occurs discretely. And these softwares are like Extend is what Y12 uses. MATLAB has a package, there's Simulate, there's Simio, there's a million of them out there. All you have to do is Google discrete event simulation, you'll come up with a bunch of them. But they're excellent tools to model these kind of processes. And so one of the things I did for Y12 was I was modeling a process, and this is the one where I talked about the data, where they had, in this case, they had 4 machines that could be working or not. And their data they had for me about failure rate, they wanted me to model throughput and include failure rate. And so the first approach people always think of is, well, I need to know mean time between failure and mean time to repair, and put that in my discrete event simulation. Well, when they handed me the data, that was what said they had a counter with a big X on it on the days that machines were broken, and a little number on how many were broken. And well, that's not bad though. Yeah, you didn't measure how long it took to repair or which machine it was, but at least you're telling me a discrete distribution, right? You're telling me each morning how many machines I have. So from that, I could come up with a probability of your machines being broken and make myself a discrete distribution. And so what I did, I just had the simulation software every morning in the model. You know, the morning didn't really occur, but every morning go ask the distribution, how many machines do I have today? And if it was 3, well, I would only allow in the logic 3 machines to be working. If it was 1, I would only allow 1 to be working that day. And so I could do that, and it worked very well. You know, on the average, you know, on a day-to-day basis, yeah, it's wrong. Because you know, you're never going to have a situation where today I have 1 machine and all of a sudden tomorrow I have 4, because you can't repair 3 of them overnight. But in the aggregate, if you're looking at throughput for a quarter or for a year, and of course that's fine. You know, so who cares if it jumps from 1 to 4 to 3 to 2, and it was really, you know, 2, 2, 2, 3, 3, 3. The average will still look fine. And so that's how I used it. So I'm trying to ask myself, my event of interest is how many machines are operating, or look at it the other way, how many machines are broken, and my probability depended on what I got out of the counter. So in this case, this is what it would look like if there was a 50-50 chance of a machine being broken. Now, I did this because this is completely logical, I think, right? This is no machines working, 1 machine working, 2 machines working, 3 machines working, 4 machines working. So if it's a probability of the machines breaking is kind of 50-50, and then I can get them fixed overnight, you would expect that on the average I'd have 2 machines working if I had 4 on my floor. You know, every other day one's going to be broken, and so my average should be 2. Well, let's play with it a minute, right? What if, and you'll like this, I think, what if I only have a 95% chance of my machine being working? My pi is the machine working. Let's do that. Oh yeah, that's exactly what you would expect, right? Look how it changed. It's almost, most of the time, I have 4 of them working. Yeah, and the possibility that I have none of them working was darn near 0. Yeah, because I got good machines. They're 95% available. I got that off the counter, right? And vice versa. Let's go the other way. Let's say I only have a 10% chance of my machines being working. You know what it's going to do? Yeah, you plop that way. And so you can see how this distribution works now, I think, once you start playing with it. And I can put anything in between. Let's put something sort of like 30% or something. Yeah, skewed down to the bottom, but so in general, kind of the averages, I had 1 machine working. And so you can see how this is a useful distribution. And so you can get a little insight, a little feel, like I said, if it's a bigger number over here, it's going to skew it to the right. Yeah, it's 75. And the way this is calculated in Excel is, of course, very brainless, and it was in the book too. It's just binomial dist, or binom dist, or binom.dist if you got a newer version of Excel. And the number you want, the number of samples, and probability, and you don't want it to be cumulative. You want each discrete distribution. So keep that in mind now. So that's how you use it. Now let's go back here. Come back to that. So now, let's see. So now they're going to ask us, what's the probability of 1 success in 5 if the probability of event of interest is 0.1. So this is similar to mine when I put 0.1 in. I had one success and 4 was mostly probable, I think. So 5, they got one more machine there. So they got 5 samples. You want to know what's the chance of the success of just getting only one when it's a 10% chance of success. So it's written this way. What's the probability that x equals 1 given I have 5 samples and my probability of success is 0.1? Here's the probability of failure. Yeah, you have 4 failures, 1 success. That's the total number. It comes out 33%. That's what we saw almost on that graph, right? That this sort of was taller. The others were, the others were 10, 20%. So here's the keys. Let's see. This is your number of samples, right? That's the number of successes. That's the probability of success, and that's all you needed, right? Yeah. Oh, and yeah. So there's your X, number of successes, total number of samples, and probability of success. So let's see. Yeah, oh, they got another example. Yeah, that's good. So the probability of purchasing a defective computer is 2%. So what's the probability that I get 2 defective computers if I purchase 10? Okay, so what's the probability that I get 2 defective computers given that I've sampled a pile of 10 of them, and my failure rate, or my success rate, you see, I shouldn't use the word success rate, my rate of, my probability of buying a defective one. I don't think buying a defective one is a success, but that's what we're trying to ask, right? So I want to buy 2 defective ones. I'm asking myself, what's the chances I get 2 defective ones? I bought 10 when there's a 2% chance in the whole world of the computers that I'm buying of getting defective ones. So 2 is going to go in here. It's going to go up here. 0.2, 0.8, 0.08, or 0.98. Yeah, very low. Yeah, that makes sense, right? Very low chances that I'm going to get 2 in a row, or not 2 in a row, but 2 out of 10. And when you do the math too, if you wind up doing this, the Excel does the binomial distribution. Oh, it's food time, yeah. So that we'll take a break in a minute. If you do this math by hand, notice that most of these divide out, right? 10 factorial divided by 8 factorial is 10 times 9. So you can do some quick math. Although the Excel does it for you. If you don't want to do it on your calculator. And then they have a couple of pictures of it for you too. Let's see. There was the n equal 5 and the 0.1, n equal 5 and the 0.5. So that's what I did for you with 4, right? So again, and the only difference with when you had an odd number, look, at 50-50, those two are equal instead of one tall one in the middle. So I think you can start seeing it, start getting a feel for this distribution. Yeah, this is good. This is a perfect place to break because I was going to pull up the June babies thing here just to remind me, and then show you that they made a mistake on here, so that's good. So we grab our food, we'll take a break. I'll pull up the June babies, and that's a perfect thing to talk about while you're first starting to eat. So yeah, grab your food, take a break. I'll get June babies up here.
My dad was born I don't know anybody born four. Thinking on the other end of that.
June babies thing.
Oh, there you go. I'm saying my daughter's. That's her book. Yeah. And I don't have. It's a little smaller.
Yeah.
And I'm taller than my dad. But I got a lot of the other stuff. Brain. He's a busy father. The brain. He's Latino. My mom kind of screwed that. I'm sorry.
Yeah.
So,
That's good. Sit down. That's good.
yeah. Well, I mean, you don't see many left-handed people, so most of them, when they're out on a floor
Right,
or a
right.
court, on a basketball, soccer, or whatever, people skew to one side, not expecting to go that way.
Instead of having to calculate when I put like the part that
Play to, I usually play people that are non-dominant. Forces them to use the non-dominant.
I was trying to
No,
Put them in
figure
a
out
position. where
Which
they
ones
want to
were?
go.
deviated most from what it was supposed to be.
Yeah, I can show you how to do that.
No, I did the long like cell which is all the standard deviation.
Yeah, you're right. You have to use their mean, yeah.
Yeah, so I calculated.
Because you might want to, because you know what it should be, right? Yeah. So you're kind of asking yourself, I guess you're kind of asking two things. So what is the mean thickness? What it should be is one question. And then after that, you're asking yourself, which ones, I guess you're kind of asking two questions. So which parts are deviate from the sample mean? Which ones deviate from the real mean? Yeah, because there could be, because they could all be dead around their sample mean, and none of them be outliers, but that mean be way off from the real mean, which, you know, I mean, your machine is adjusted.
That's okay.
I got Lucy, Steve, and Billy. She's too young now.
So you want to ask yourself, I guess, which,
How old is she? 5.
where do each of
They
them
do
fall?
that.
Mine's 4.
Yeah, if I told
But
her-
I've already instilled in her lots of. She sees people out that have ponytails, and she points out all the boys that have ponytails. Because I told her that anybody that's boy that has a ponytail is not to be trusted.
Yeah, I was in.
Boy has a ponytail. I don't want to talk to him.
Compare them.
Good, keep that
Each to the
mentality going.
Because these two are there. You have a known.
We were going over how the moon is out at night, and then the moon's out during, and then like, so the sun's at day, and the moon's at